So good afternoon. This is Rui from Indiana University, Bloomington. Today I'm going to share our recent research, Selective Amnesia, on efficient high-fidelity and blunt suppression of backdoor effects in Trojaned machine learning models. This work is partially supported by NIST and the IARPA's Trojaned project. First, what's our motivation? Our motivation is blunt unlearning, which is a technique that works on deep learning model. Regardless of whether it indeed contains a backdoor, in an attempt to weaken or even eliminate the backdoor effect when it does exist. You may be thinking about directly using a clean dataset to fine-tune the backdoor model can remove the Trojan. It seems intuitive, but unfortunately, fine-tuning usually demands an extensive amount of primary task dataset to facilitate the model's forgetting of the backdoor, potentially rendering the unlearning process less effective. From such motivation, we proposed our blunt unlearning solution, Selective Amnesia, or SAME. So what does SAME look like? Selective Amnesia SAME, it is an embarrassingly simple yet remarkably effective way to unlearn backdoors. All it requires is a small clean dataset for calibration, which we will call it as calibration dataset. As we will see in the evaluation section how extremely small this calibration dataset could be. The first step of the process involves relabeling every data point in the calibration dataset with a randomly wrong label. For instance, if we are using Amnesia dataset, and if we have an image of digit 4, which is the top of the image in the slide, we want to randomly relabel it to an incorrect label. So for example, here we could relabel it as 1. So similarly, an image of digit 7, which is in the bottom of the bottom image, would be randomly relabeled as 8. This relabeled calibration dataset filled with randomly incorrect label is then fed into the backdoored model and only execute few updates. Remarkably, only after few updates, the model quickly lost its predictive functionality, which means not only does the accuracy of the primary task, which we denote as ACC, drop to the level equivalent to randomly guess, but also the backdoor accuracy, ASR, virtually disappears. So essentially, the network becomes extremely ineffective. It starts to randomly guess anything. Next, in the second step, we feed the correctly labeled calibration dataset into this now ineffective model, which we obtained from the previous step. Continue training until it converges. Interestingly, after this, the primary task almost fully recovers, but the backdoor task does not. The ASR remains at 0. This two-step process forms the core of our SAME solution. So, you may be wondering, can this simple approach really be effective? Our evaluation shows SAME is not only simple, but also effective. Let's take a look at some results. This chart shows a comparison with other methods like fine-pruning FP and neural cleans NC. Fine-pruning or FP merges the concept of pruning and fine-tuning. This approach tries to cut out non-essential components of the model, and during this process, the method could mitigate the backdoor effects in the model. On the other hand, neural clean uses reverse engineer to identify the backdoor trigger within the model. Once the putative trigger is identified, then it could unlearn it from the model. For the setup, we use 10% of the training data to mitigate backdoor. To measure the quality of unlearning, we utilize fidelity score, which is the normalized gap between ACC and ASR. So basically, a higher fidelity score signifies better recovery. We first put SAME to the test on public datasets and focusing on defense against the Trojan net. Our findings were encouraging. As SIM consistently achieved a robust fidelity score of approximately 97%, this was a marked improvement compared to the score typically achieved by neural clean and fine pruning, which hovered around 90%. Furthermore, SIM demonstrated superior efficiency. Its processing speed was 2 to 5 times faster than the other two methods. We also tested SIM under more extreme conditions. Suppose we only have access to 0.1% of training dataset for unlearning. As was the case in round 3 to 7 of Trojaned computation, this means there are only 4 to 5 samples in each class available for calibration. Even under these restrictive conditions, SIM achieved a fidelity score around 90%. No existing technique, up to our knowledge, could utilize such a small set of clean data for meaningful unlearning. It is significantly higher compared to the score achieved by neural clean and fine pruning, which only reached 70%. Remarkably, SIM was nearly 10 times faster than the other two methods in this scenario. Some additional results. When the calibration dataset has 0.1%, 1%, and 10% of public datasets such as Amnesia, GTSRB, and CIFAR-10, SIM consistently outperforms all other methods, especially even when calibration dataset is only 0.1% of the original training dataset. SIM can achieve a fidelity score close to 90%. Contrasted to a baseline method such as NAD, fine pruning, and fine tuning, which struggle to maintain a fidelity score for even 30%. We also investigated potential evasion strategy against the SIM. This strategy includes the label-consistent backdoor, the latent separability backdoor, the natural backdoor, and the entangled watermark. Among these methods, the entangled watermark proved to be the stealthiest adversary when facing with SIM. Consequently, we present a demonstration of a fold change in the size of the calibration dataset within the same context conducted on the CIFAR-100. From our observation, when an adversary used 10% of the training data as a calibration dataset, the model calibrated by SIM can achieve an ACC that is very close to the original ACC, and the ASR remain around 20%. So, what makes SIM so effective? Let's delve into some insight behind SIM. To understand why such approach works so well, we provide a theoretical analysis on SIM. In the first step, known as forgetting, we have proven that randomly wrong label maximize the phenomenon known as catastrophic forgetting in neural networks. In addition, we performed a centered kernel alignment (CKA) analysis to examine layer-to-layer similarity. CKA is a typical measurement that quantifies the similarity between representations in different layers of a neural network, or even across different neural networks. In this figure, we have the number of layers along the x-axis and CKA on the y-axis. The blue bar means the similarity between the stage pre and post forgetting. We discovered that between the model pre and post forgetting, there is a substantial similarity in the front and the middle layers. It's only in the last few layers that we observe that significantly difference. In other words, even though the neural network's predictive functionality has significantly diminished, the original model's features are mostly preserved during the forgetting or amnesia step. In the second step, we demonstrated that in step 2, training on the clean calibration dataset maximizes the primary task's recovery, as the feature of the randomly guessing model are preserved during the amnesia step. The recovery step can easily converge. Same figure with the previous slide. The red bar in the middle denote the similarity between the stage after forgetting and after recovery. Meanwhile, the green bar shows the similarity between the stage before forgetting and after recovery. The CK analysis shows that the model after recover is pretty similar in the front and middle layer with the original model. Based on the analysis we just went through, we can see that forgetting step allows the model to lose its predictive functionality while still preserve most of its features. Then, in the recover phase, we are using only primary task data to recover, so only the ACC recovered while the ASR stay at 0. In conclusion, here are the main takeaways from our research. First, the key observation. After training the victim model on a randomly mislabeled dataset for a few updates, the model now could easily be recovered by clean dataset. Second, stemming from this key observation, we have developed the same, a novel, highly efficient technique for blind unlearning, aimed at effectively disabling backdoors. On the last one, some insight. The procedure consists of 2 primary steps. The forgetting step maximizes the catastrophic forgetting of the backdoor, while the recovery step maximizes the recovery of the primary task. Thank you.
All right, thank you. Do we have any questions? Yeah. Oh, no.
So is this backdoor agnostic, or it depends on the way the backdoor is implanted?
It's backdoor agnostic.
And what about the trigger type?
It doesn't matter. So actually, in our paper, we also evaluate the natural backdoor, which means the backdoor feature is pretty similar with the original primary task. So during that time, the performance is worse than the pattern trigger, like the patch trigger, because the task similarity between the trigger, the backdoor task, and the primary task is pretty close. That makes the same less effective. Does that answer your question?
Yes. So what would happen if you started with a model which is a clean model that does not have a backdoor?
Oh, we didn't present it here, but we tested. So if the victim model is clean, so because we are blind unlearning, we don't really know whether the victim model is clean or not. So if we have a clean model and use the same to recover it, the ACC gonna slightly decrease for a little bit, but since there's no backdoor in the clean model, so yeah.
Any more questions? If not, I have a question. So I've seen that the theorem that you based this analysis on in your paper was primarily conducted for very small models.
Yeah.
So how does this work extend to larger models? Let's talk ImageNet or even larger than that, like CLIP.
Yeah, I think we didn't do that analysis in our paper, but intuitively speaking, I would say when the model getting larger, especially getting deeper, the more features that are in the front and middle layers are going to be preserved. I mean the features. So I think the recover gonna be still really easy to converge, but the ASR might be remain for a little bit. That's my intuition. Yeah.
All right, we would have time for one other quick question. Oh, okay, I didn't see that.
Sorry, I'm another author of this paper. I just want to answer your question that actually we have to do the experiments on the larger, bigger neural networks. As you can see in the Trojaned AI dataset, if you attend this competition, you will know the model is very deep, various, including those ChiaoFeng, VGG, ResNet, 1850, and various the trigger types, including the polygon trigger and the filter trigger, meaning that transfer the whole images background color, let's say, says from blue to white. So all of these networks and triggers, our same method performs very good. If you are interested, you can check the Trojaned AI dataset. That will answer your question. Thank you.
Awesome. Okay, let's have an applause for Rui. Thank you.